Action potentials are always considered to be all or none events. This means it either goes or it doesn't go. It's like when you fire a gun, you pull the trigger. Either the gun fires or it doesn't fire. It doesn't fire halfway. It doesn't fire partially at all. It either fires completely or it doesn't fire. And that's the way action potentials are. An action potential is a propagated change in the membrane potential that affects the entire excitable membrane. Now, keep in mind that the neuron receives information at the dendrite or cell body, but at the far end of the neuron, at the axon terminal, it releases the neurotransmitter. So something has to connect the graded potential at the cell body with the release of the neurotransmitter, and that's the action potential. There are quite a few channels involved in this. Mostly we'll see voltage-gated channels. Resting membrane potential depends on leak channels. The graded potential depended on chemically gated ion channels. And these action potentials depend on voltage-gated ion channels. So we'll go through the steps of generating an action potential. Remember, the membrane is, there's a resting membrane potential. And when it's resting, the voltage-gated sodium and potassium channels are both closed. There is a stimulus and a graded depolarization that opens up the voltage-gated sodium channels. Sodium enters. The channel opens up at threshold, which is about -60 millivolts. So once the graded depolarization is large enough at -60 millivolts, it will open the voltage-gated sodium channels. And this is going to cause a huge rush of sodium ions into the cell. This causes a very rapid depolarization where the membrane potential rises from -60 to a positive value. Again, this is an all or none principle. Any stimulus triggers an action potential or does not trigger an action potential. And all stimuli that bring the membrane to threshold result in an identical action potential. There are no small action potentials or large ones. They're all exactly the same. Step 3 is inactivation of the sodium ion channels and activation of the potassium ion channels. Remember, sodium was rushing into the cell, and the membrane potential reached a positive value of +30 millivolts, and that's going to trigger the sodium channel inactivation. At the same time, the voltage-gated potassium channels will open, and potassium will leave the cell. As potassium leaves the cell, it takes away these positive charges, and so the membrane is going to go back to its resting membrane potential. This return to normal is called repolarization. Then the potassium ion channels close, and basically the membrane potential returns to near normal. There's a little bit of hyperpolarization as the membrane potential, as the membrane potential reaches -70 and those voltage-gated potassium ion channels begin closing. There's a brief period of hyperpolarization. There is a refractory period. There's an absolute refractory period during which the membrane cannot respond at all to a stimulation. And during the relative refractory period, if the stimulus is larger than normal, then the membrane can respond. So here is the time in milliseconds of this action potential. And on the y-axis, you see the membrane potential. So our membrane starts a resting membrane potential of -70 millivolts. There's a graded depolarization, and that small area of excitable membrane is brought to -60. This is going to cause those voltage-gated sodium channels to open, and sodium absolutely rushes in, and there's a great quick depolarization of the membrane. Then the sodium channels close, and the voltage-gated potassium channels open. So potassium leaves the cell, and repolarization occurs. The voltage-gated channels begin closing. Near threshold, the voltage-gated sodium channels begin reactivating, and the membrane soon returns to its normal resting state of -70.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body, in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of -70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only, and the membrane potential returns to the resting state of -70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of -70 millivolts.
Which step occurs first in the generation of an action potential? Voltage-gated sodium ion channels open.